Hello everyone, I am Dr. VRAO. In the last video, that is in the lecture 38, we had gone through the concept of electrolysis and construction of electrolytic cell, and from that lecture we came to know that electrolysis is nothing but decomposition of a chemical compound into its constituent elements by the passage of EMF, and we discussed the examples, that is electrolysis of molten KCl and electrolysis of aqueous KCl. Okay, today I shall give some more examples. Electrolysis other examples are aqueous K2SO4 potassium sulfate. If we electrolyze aqueous solution of K2SO4 potassium sulfate, let us see what are the products that we obtained at cathode and anode. At cathode and at anode, right? Electrolysis of aqueous K2SO4, if we electrolyze aqueous solution of K2SO4, we get H2 gas at cathode, H2 gas at cathode and O2 gas at anode, O2 gas at anode. Let us see another example, aqueous solution of KCl, right? Aqueous solution of KCl, we get H2 gas at cathode and Cl2 gas at anode, Cl2 gas at anode. And let us see another example, that is fused NaCl, fused NaCl solution. Okay, you mind this point, fused NaCl is not a aqueous solution, right? Already I told you the fused state, I already explained the fused state and importance of that fused state, right? Fused NaCl, if we electrolyze fused NaCl, we get sodium at cathode and Cl2 gas at anode, Cl2 gas at anode, right? Let us go for another example, fused NaOH. If we electrolyze fused NaOH, sodium hydroxide, we get sodium at cathode and O2 gas at anode, O2 gas at anode. Okay, and let us go for another example, aqueous solution of CuCl2, cupric chloride, aqueous solution of cupric chloride. If we electrolyze aqueous solution of cupric chloride, we get copper at cathode and Cl2 gas at anode, right? Cl2 gas at anode. And let us go for another example, aqueous solution of copper sulfate, aqueous solution of copper sulfate. If we electrolyze aqueous solution of copper sulfate, we get copper at cathode and O2 gas at anode, O2 gas at anode. Okay. After seeing these examples, you may have doubt how can you write how I am writing the products at cathode and products at anode. You may have doubt how can he writing the products, right. So, there is a rule for writing the products at respect to cathodes and anodes when we electrolyze some chemical substance. What is that law? What is that law? If metal is more reactive than hydrogen, then hydrogen is liberated at cathode. I repeat, okay, you after seeing these examples, you have a doubt how can sir writing all the products at cathode and anode. Okay, there is a law for writing the products formed at a cathode and products or gases or substances liberated or deposited at a cathode and anode. That law is okay, if metal is more reactive than hydrogen, then hydrogen gas is liberated at cathode. I repeat, if metal is more reactive than hydrogen, then hydrogen gas is liberated at cathode. Another statement is, if hydrogen is more reactive than metal, then metal is deposited at cathode. I repeat, if hydrogen is more reactive, then metal is deposited at cathode. Okay. So, you have to remember these two statements in your mind. Okay. You have to keep these two statements in your mind. Okay. I repeat, if metal is more reactive than hydrogen, then hydrogen gas is liberated. Let us see the example. Here if you electrolyze the aqueous KCl solution, aqueous KCl solution means there is a water, the aqueous KCl solution, that means there is a water molecules in the water as solvent. Okay. So, if we electrolyze KCl solution, okay, metal is more reactive than hydrogen. Metal is more reactive than hydrogen. That's why instead of potassium, hydrogen gas is liberated at cathode. Right. So, if you please keep this point in your mind, that is, if metal is more reactive, if metal is more reactive than hydrogen, then hydrogen gas is liberated at cathode. Okay. Alkali and alkaline earth metals are more reactive than hydrogen, right. Next, and another statement is, if hydrogen is more reactive than metal, if hydrogen is more reactive than metal, then metal is produced or metal is deposited at cathode. Let us see the example. If you electrolyze the aqueous solution of cupric chloride, if this copper metal is less reactive than hydrogen. So, that is why hydrogen is reduced the copper metal, that is why copper metal is deposited at cathode, because copper is less reactive than hydrogen, right. Copper is less reactive than hydrogen. How can I know, or how would we know whether the metal is more reactive or hydrogen is more reactive? Okay. Let us let me pose a question. How can we know whether the metal is more reactive or hydrogen is more reactive? Okay. The answer is, we can know, we can know the whether hydrogen gas is more reactive than metal, or metal is more reactive than hydrogen, and we can know that from electrochemical series. Okay, electrochemical series. Okay, I shall explain the electrochemical series in the later classes, right. So you should keep one point in your mind. Okay, what is that point? If metal is more reactive than hydrogen, then hydrogen gas is liberated. If hydrogen is more reactive than metal, then metal is deposited at cathode, right. So these are the some more examples of electrolysis. Okay, in this all these examples, electrodes are, and cathode and anode are platinum electrodes. Cathode and anode are platinum electrodes, right. Okay, so scientist Faraday, Michael Faraday, conducted number of electrolysis experiments, right. Michael Faraday conducted a number of electrolysis experiments, and based on that experiments he formulated two laws, though that two laws are called as Faraday's laws of electrolysis. Faraday's laws of electrolysis, and these laws deals with the mathematical relation between quantity of electricity passing through the electrolyte and quantity of substances that are produced or liberated or deposited at respect to electrodes, right. So let us see that Faraday's laws of electrolysis, right. Right. Faraday's laws. Faraday's laws of electrolysis. Okay, let us see. Already I told you Faraday's laws deals with mathematical relation between quantity of electricity passing through the electrolytic solutions and quantity of substances deposited or liberated at an electrodes or at respect to electrodes, right. Okay. So Faraday's first law is first law of Faraday. First law, Faraday's first law. This law states that the mass of substances, deposited at an electrode, the mass of substances deposited at an electrode during electrolysis is directly proportional to the quantity of electricity passing through the electrolyte. Okay, you all are familiar with this statement. Okay, so what is the statement? I repeat, the mass of substances deposited or liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passing through the electrolyte solution, right. That is quantity of substance deposited or liberated at an electrode, that is being represented by M. Okay, mass. So mass of substance is being represented with M. So the mass of substance deposited at the electrode is directly proportional to the quantity of electricity passing through the electrolyte during electrolysis. So quantity of electricity is being represented with Q. Okay, so mass of substance deposited at the electrode is directly proportional to quantity of electricity passing through the electrolyte during electrolysis, right. So if we remove this proportionality, okay, M is equal to some constant E into Q. Okay. So, this E is called proportionality constant, and usually we call it this constant as electrochemical equivalent, electrochemical equivalent, electrochemical equivalent, electrochemical equivalent. So, electrochemical equivalent, we can define this electrochemical equivalent, that is E is equal to m by q. Okay, E is equal to m by q. So, electrochemical equivalent is a ratio of m to q. Okay, I repeat, electrochemical equivalent is a ratio of m to q. Okay, so ratio of m to q is called electrochemical equivalent. So, where m is in grams, so mass in grams and quantity of electricity in coulombs. Okay. So, electrochemical equivalent is defined as mass in the mass of substance deposited in grams for the passage of 1 coulomb of electricity. Okay. So, electrochemical equivalent is mass of substance, okay, mass in grams, okay, mass in grams deposited at the electrode, deposited at an electrode for the passage of 1 coulomb of electricity, right. Okay. And electricity coulomb, so coulomb q, and we know that from the earlier classes, that is from before SSC, we know that the quantity of electricity q is q is a unit, coulomb is a unit for expressing the electric charge. Okay, q means coulomb, coulomb is a unit for electric charge. Okay, electric charge. Already in electrolysis we are passing EMF. EMF is nothing but electromotive force. We are passing electromotive, that is we are passing electricity, that is electricity means flow of electrons. Electrons have charge, electrons have charge. Okay. So, q is a product of, from earlier classes we know that q is a product of current in amperes, see current in amperes, and time in seconds, t in seconds, t in seconds. So, q is a product of c into t, q is a product of c into t. So, current in amperes, time in seconds, this product will give coulomb q. Okay. So, we can replace this q with Ct, that is m is equal to E C T. So, mass of substance or gas liberated at an electrode during the hydrolysis is equal to ECT. Okay, where E is electrochemical equivalent, C is current in amperes, T is time in seconds. Okay, but we know that E is electrochemical equivalent, E is a ratio of m to q, that is mass in grams, quantity of substance or mass in grams of chemical substance deposited for the passage of 1 coulomb, for the passage of 1 coulomb. So, mass in grams, okay, mass in grams deposited for the passage of 1 coulomb electricity. But in chemistry you should keep this point in your mind. Okay, in chemistry it is customary to express the quantity of substances in moles. That is why we are using moles, mole concept. Already I told you in the first class of my lectures. Okay. So, it is quantity of chemical substances. It is customary to express the quantity of chemical substances in moles. Okay. In chemistry, it is a customary to express the quantity of substances in moles. So, mole is the unit to express the quantity of chemical substances, but here the quantity is expressed in grams. Okay. So, we use it to express the quantity of substances in moles. That is why we shall go for another unit, that is in grams. We shall convert this is the mass in grams, this is the mass in grams for the passage of 1 coulomb of electricity, and coulomb is a unit for expressing the electric charge. Coulomb is a unit for expressing the electric charge. Okay. But chemical substances are expressed in moles. So, for the electric charge carried by 1 mole of substance is called Faraday. Okay. So, Faraday is Avogadro number into electric charge, that is electric charge. Faraday's constant, Avogadro's constant, we know that Avogadro's constant 6.023 into 10 to the power of 23, and the charge of electron is 1.6 into 10 power minus 19 coulombs. Okay. So, after multiplication of these two values, we get 96,500 coulombs. Okay. So, 1 Faraday is equal to 96,500 coulombs, right. So, 1 Faraday is the charge of 1 mole of electrons. Okay. Faraday is charge of 1 mole of electrons. Okay. So, but coulomb is but electrochemical equivalent is mass of substance in grams deposited for the passage of 1 coulomb of electricity, but for 1 mole of electrons electric charge is equal to 1 Faraday, right. So, let us if we pass 96,500 coulombs, during the electrolysis, we get 1 mole of substance. But here if we pass 1 coulomb, for the passage of 1 coulomb of electricity, we get the substance in grams. But if we pass 96,500 coulombs during the electrolysis, that is 1 Faraday, we get 1 mole of substance. So, let us remove this electrochemical equivalent from this equation. Okay. That is M is equal to, therefore, M is equal to, if we remove this electrochemical equivalent with chemical equivalent, if we pass 96,500 coulombs during the electrolysis, that is called the amount of substance that is deposited at the electrode is called chemical equivalent. So, that is E is replaced by E by 96,500 into C into T. Okay. No need to confuse, there is simple. Here we are removing this electrochemical equivalent with chemical equivalent. Electrochemical equivalent is the amount of or mass of substance in grams for the passage of 1 coulomb electricity, but chemical equivalent is amount of substance deposited for the passage of 96,500 coulombs. If we pass 96,500 coulombs, we get 1 mole of substance. Okay, so 96,500 coulombs. Okay, so if we remove the electrochemical equivalent with chemical equivalent. Okay, so E by 96,500 coulombs. Okay, so where E is called chemical equivalent, where E is called chemical equivalent, E is called capital E is called chemical equivalent. E is called chemical equivalent. So, we can replace this electrochemical equivalent with embedding the E by 96,500 in this equation. We can eliminate the electrochemical equivalent from this equation. Okay, and we know that chemical equivalent, we know the formula for chemical equivalent. Chemical equivalent, we know this concept from the earlier classes. Chemical equivalent chemical equivalent is atomic weight of substance, atomic weight of substance by its valency, its valency. Therefore, we can write mass of substance deposited at the electrode, mass of substance deposited at the electrode, M is equal to ECT. If we remove this electrochemical equivalent with E by 96,500 into C into T, and if we remove this E chemical equivalent with atomic weight by valency by 96,500 into C into T. Okay, therefore, we can write this as atomic weight by valency into 96,500 coulombs into C into T. Therefore, M, the mass of substance deposited or liberated at respect to electrode is equal to atomic weight by valency into 96,500 coulombs into C into T. Now, we are getting the mass of substance in moles, right? Okay. Now, let us go for Faraday's second law. Let us go for Faraday's second law. Okay, and next Faraday's second law of Faraday. Okay, so this you all very well know about this statement of Faraday's second law. Okay, if same quantity of electricity passing through the different electrolytic cells connected in series containing different electrolytes, then the mass of substances deposited at the respective electrodes is directly proportional to chemical equivalents of that substances, right? I repeat, if same quantity of electricity is passed through different electrolytic cells or electrolytic containers or electrolytic cells containing different electrolytes connected in series, then the amount of substances deposited at the respective electrodes is directly proportional to the chemical equivalents of that substances. Okay, let us go for that example. Okay, if we take 3 electrolytic cells, one electrolytic cell, we know that electrolytic cell is a container, electrolytic cells, 3 electrolytic containers. For constructing the electrolytic cell, we need 3 containers and we need 2 electrodes for electrolytic cell. this is another electrode, okay. So, these are 3 electrolytic cells. These are the 3 electrolytic cells connected in series. This is positive electrode, negative electrode, positive electrode, negative electrode, positive electrode, negative electrode, right? That is cathode, anode, okay, connected in series. If we connect to the battery, positive charge connected to the long line, negative electrode connected to small line. This indicates positive and small line indicates negative, right? Right. Connected in series. This positive negative is connected to positive and this negative is connected to positive. So, these are the 3 electrolytic cells connected in series. These are 3 electrolytic cells connected in series, right? Then now we are taking 3 different electrolytes in which copper sulphate, okay, in which AgNO3, in which H2SO4, So, according to the statement, if the same quantity of electricity passing through the different electrolytic cells connected in series containing different electrolytes, then the quantity or the mass of substances deposited respect to electrodes, that is cathode and anode, the mass of substances deposited at respect to electrodes is directly proportional to chemical equivalents of that substances, right. So, same quantity of electricity, same quantity, 1 Faraday or 1 Coulomb or 1 Faraday electricity, 1 Faraday electricity passing through these 3 electrolytic cells, okay, then mass of copper deposited is equal to mass of copper deposited at cathode is directly proportional to chemical equivalent of that substance, okay, and mass of O2 gas deposited at the electrode is equal to chemical equivalent of that O2. So, if we remove that constants, we can write the fraction, we can write this ratios. Mass of copper is equal to chemical equivalent of copper and mass of oxygen is equal to chemical equivalent of O2 gas, right, and mass of Ag by mass of O2 gas. So, mass of Ag is equal to a chemical equivalent of Ag by chemical equivalent of O2, okay. So, mass of Ag is directly proportional to chemical equivalent of Ag and mass of O2 is directly proportional to chemical equivalent of O2. If we remove that proportionality and proportionality constants and we can rearrange this equation, we can write this as, like this, right, and mass of H2 by mass of O2 is equal to chemical equivalent of H2 by chemical equivalent of O2. So, this is the second law of Faraday. So, if we pass same quantity of electricity through different electrolytic cells connected in series containing different electrolytes, the mass of substances deposited at the respective electrodes is directly proportional to the chemical equivalents of that substances, okay. from let me conclude this lecture. So, electrochemical equivalent is nothing but mass in grams deposited, mass in grams of chemical substance deposited at the electrode for the passage of 1 coulomb of electricity. Whereas chemical equivalent is mass in mass of substance, usually in moles, mass of substance deposited at the electrode for the passage of 1 Faraday of electricity. That is the difference between electrochemical equivalent and chemical equivalent. Electrochemical equivalent is the mass of substance deposited at the electrode for the passage of 1 coulomb electricity, but chemical equivalent is amount of substance deposited at the electrode for the passage of 1 Faraday of electricity. Okay, these are the two laws of Faraday, and these laws are very much useful, and there is n number of applications for this Faraday's laws. These Faraday's laws can be useful for investigatory applications and preparatory applications, right. These applications and this technique is useful for the determining the mechanism of chemical reactions, and this technique is useful for extraction of metals. Okay, in metallurgy we are in nowadays in metallurgy with the and we will learn that metallurgy lesson. In that lesson we are extracting metals from their from their raw materials. Okay, so extracting the metals from their sources and we can with the help of electrolysis technique we can extract the metals from their sources, right. And this electrolysis technique is useful for determining the mechanism of chemical reactions, right. So, there are n number of applications for electrolysis technique. Okay. In the next video I shall come up with galvanic or voltaic cells. Thank you for watching.